June 3rd, 2026. The sky was calm. Then one of the most extraordinary visitors in human history was detected. At precisely 0317 UTC, the Deep Space Surveillance Array of the James Webb Space Telescope noted a faint but distinct object on a trajectory unlike any known minor body. The signal came not from the ecliptic plane where the familiar comets and asteroids roam, but from high above, plunging inward on a steep curve toward the Sun. Within hours, the orbit was confirmed: a hyperbolic path, excess velocity, an origin clearly outside the solar system. The object was soon catalogued as C2026 H1, the first confirmed macroscopic interstellar visitor of 2026. The discovery came as a surprise. Survey systems such as the Asteroid Terrestrial Impact Last Alert System, ATLAS, and the Vera C. Rubin Observatory had been optimized for near-Earth objects and standard long-period comets. But here was something different. A body arriving at nearly 60 kilometers from a direction roughly aligned with the galactic plane, inclined by some 70 degrees relative to the solar system's plane. The hyperbolic excess velocity, v, measured at about 55 kilometers, left no reasonable doubt. This was an interstellar object. Almost immediately, the global astronomical community swung into action. Professional observatories mobilized their largest instruments. Amateur astronomers trained their backyard scopes on the point of arrival. Multiband photometry, spectroscopy, and dust coma imaging were logged within days. What emerged was an object that behaved in some ways like a comet: icy, outgassing, a visible coma, and tail, but in other ways entirely unlike any comet previously studied within our solar system. Initial measurements revealed a nucleus brightness around magnitude 8, visible to reasonably equipped amateur telescopes under dark skies. The tail extended nearly 3 degrees, an astonishing length for a fresh interstellar visitor. Its coma exhibited a reddish dust signature, reminiscent of previous interstellar object 1I Oumuamua, 2017, and 2I Borisov, 2019, but the volumetric outgassing rate was far higher. This object was not merely passing. By any standard, it was dominating its local environment. Here are the key data points. Its perihelion was calculated to occur around August 9th, at a distance of 0.75 AU from the Sun, inside the orbit of Venus. The orbital inclination hovered around 68 degrees, and the eccentricity exceeded 1.8. The object's direction of approach was from the galactic sector of Tucana Indus, unusually aligned for a body arriving from outside the solar system. The detection window before perihelion was extremely narrow, less than 60 days from discovery to closest solar passage. For astronomers, the clock had begun ticking. But the real intrigue came from the chemical and dynamical anomalies. Spectroscopic observations utilizing the near-infrared spectrograph aboard Webb and complementary ground-based data revealed an unexpectedly high ratio of CO2 to H2O, approximately 6.1, a chemical signature more extreme than that of Borisov, and suggesting formation in a very cold or chemically distinct environment. Nickel vapor lines were detected, though marginal, and dust grain albedo appeared higher than typical cometary nuclei. Some teams flagged reflective metallic-like specular glints from the nucleus, prompting informal comments such as "shiny core" in observer chat rooms. The tail's morphology also puzzled observers. Rather than a smooth, steadily expanding dust tail, the structure showed episodic brightening events every 12 days, each coinciding, astonishingly, with subtle shifts in tail angle of 0.4 degrees. These were tracked independently by multiple amateurs across Europe and Australia. The working explanation among specialists: strong non-gravitational accelerations, far in excess of what standard outgassing models predict for a nucleus of this size. A published analysis of a similar interstellar object recently suggested that even modest accelerations merit scrutiny. Meanwhile, the professional journals began to fill with papers and preprints. One flagged the age estimate of C2026 H1 at potentially 8 to 10 billion years, based on galactic trajectory modeling and isotopic constraints derived from dust continuum observations. If true, this object predates the solar system by a wide margin. It may have been ejected from its parent system long ago, wandering the Milky Way until finally intersecting our sun's path. The timing of the arrival also raised eyebrows. The inner solar system was already preparing for the appearance of another incoming body, C 2026 K2, a long-period comet discovered a month earlier, approaching perihelion within a week of C 2026 H1 and from an entirely different sky vector. Both objects were expected to pass the Sun in mid-August, one from the northern ecliptic arrival vector in Hercules, the other from a southern approach near Capricornus. The statistical odds of two massive inbound bodies from different origins arriving so closely in time, and both visible to ground observers, were vanishingly small, and the fact that the major ground observatories would be in solar conjunction during part of that interval meant the critical perihelion window would be partially blind. The geometry was right out of a cosmic thriller. At 8 million kilometers from the Sun, C 2026 H1 showed signs of active brightening, as dust jets were observed by the 2.2-meter telescope at Calar Alto. The jets flared with a periodicity of 11.7 days, matching the tail shifts. Whether this periodicity came from nucleus rotation, internal venting cycles, or something more exotic remains debated. In any case, the rapidly intensifying tail and coma caught the attention of major institutions. Radar teams were placed on standby. High-resolution imaging campaigns scheduled to resume once the object cleared the solar glare were locked in. As the perihelion date drew near, rumors of agency restrictions began to surface. Internal memos referenced a data blackout from August 4 to August 11th, an interval that exactly overlaps the least observable period for ground telescopes as the object moved behind the Sun relative to Earth. Some observers noted that requests for time on the EastCat and Goldstone radar arrays were quietly denied, while amateur networks sent out urgent calls. Cover the blackout window. In the late-night forums, one message read, "If it disappears behind the Sun, we need you to record everything before it goes dark." And so the stage was set. Two cosmic visitors, one hypervelocity interstellar body, another long-period comet, both hurtling inward, one exhibiting behavior far beyond our standard models, chemical ratios that defy formation in a solar system-like environment, dynamical quirks that resist explanation, and a blackout window timed to the peak of activity. The question shifted from what is this object to why is it here now? The coming weeks would determine whether C 2026 H1 would simply fly past the Sun and vanish, or whether it would launch us into a question that has long hovered just beyond our reach. Are the rarest visitors merely probes of nature or messengers engineered from something beyond our current understanding? August 8, 2026. The world's solar observatories were effectively blind. For 8 days, the region of the sky containing both C 2026 H1, now unofficially nicknamed Valkyrie, and its counterpart, C 2026 K2, lay buried in the Sun's glare. It was the perfect blackout window. Ground-based telescopes shut their shutters, citing instrument safety. But outside official channels, a network of amateurs and rogue researchers refused to stop watching. From a hilltop in Chile, a radio engineer named Leon Garcia redirected an old 4-meter weather radar toward the coordinates predicted for Valkyrie's perihelion. The data stream came in noisy, flooded with solar interference. But embedded in the static, Garcia noticed a periodic fluctuation, a repeating 22-second pattern that did not match any known solar or terrestrial source. At first, he assumed it was mechanical noise. Then the same pattern was detected by a small interferometer in South Africa, and again by the Ibero tracker in Portugal. 3 independent systems, all logging a synchronized signal pulsing from the direction of the Sun. The signal was subtle, not an encoded transmission, not even modulated data, but a rhythmic variation in radio flux, faint yet unmistakably artificial in its precision. For a brief moment, the scientific underground lit up. Could the signal be a sideband reflection, a radar echo bouncing from the object's surface? Or was it something more deliberate, a beacon timed with mathematical regularity, announcing presence? Meanwhile, the official feeds remained silent. NASA's Solar Dynamics Observatory and ESA's Solar Orbiter released no fresh data, though internal logs showed that both spacecraft had recorded transient events in the same time window. When pressed, agency spokespeople cited solar storm interference. As Valkyrie emerged from behind the sun on August 14th, amateur scopes picked up something nobody expected. Not one object, but two. The main nucleus, surrounded by a smaller detached body roughly 1/100th its size, trailing it by a fixed distance of 42 kilometers. Their synchronized motion was too precise to be accidental. Photometric analysis showed that both objects rotated with identical periods, every 11.7 days, matching the earlier brightening cycle. That number, 11.7 days, sent shivers through the research community. It wasn't random. It was consistent, harmonic, as if the object's activity were governed by an internal clock. "A natural comet doesn't keep time like this," said Dr. Haruko Matsuda, an orbital physicist from Kyoto University. "If this is rotational modulation, it's the most stable we've ever seen. If it's something else new, we're staring at design." Further evidence came from the SpectraCube array in Hawaii, which caught Valkyrie's tail glowing faintly at microwave wavelengths, an emission that should have been impossible for dust or gas at its distance from the sun. Some theorized it was due to ionized plasma. Others proposed active electromagnetic confinement, like a magnetic sail. A handful dared to whisper what no one wanted to say aloud. The tail looked like an engine plume. The energy estimates were staggering. If the acceleration observed during the perihelion matched the drift data, and several teams claimed it did, then the source of propulsion would need to generate more than 20 terawatts of continuous power. That's nearly the total electrical output of Earth's civilization. But the anomalies didn't stop there. Analysis of dust samples captured by the Parker Solar Probe, which flew through the outer debris stream 2 weeks later, revealed particles unlike any seen in natural comets. Perfect microspheres of nickel-cobalt alloy uniform in size, fused with traces of silicon carbide and boron nitride, materials used in aerospace heat shielding. In other words, manufactured dust. The official report, quietly published in a supplementary appendix of a heliophysics journal, used neutral phrasing, microspherules of atypical composition. Yet among astronomers, the meaning was clear. Valkyrie might not just be an icy interstellar rock, it could be machined. By early September, the mystery deepened. The smaller companion, designated H1b, began to diverge from the parent, moving on a new trajectory angled 12 degrees off the original path. The separation velocity was measured at precisely 1.21 ms, too slow for an explosion, too fast for a gravitational drift, more like a controlled release. Observers dubbed it the drop. Theorists rushed to model what the secondary might be. Some proposed it was a fragment, a chunk of volatile ice expelled during perihelion. Others hinted it was an independent craft, a drone or probe separating to execute its own course. The object's light curve, however, told a deeper story. It flashed with a regularity of 1 Hz, 1 pulse per second, as if broadcasting. No known natural process produces such precise strobing. By now, public speculation had exploded. News outlets ran with headlines like "Alien Probe Near the Sun" and "Metallic Visitor Splits in Two." But while the public spiraled into frenzy, a quieter community of scientists wrestled with the uncomfortable truth. If Valkyrie and its companion were natural, they defied every law of cometary physics we know. And if they weren't, then something, somewhere, built them. By late September 2026, C-2026 H1 Valkyrie and its fragment H1b were receding from the sun. Yet instead of fading like ordinary comets, both objects retained an uncanny luminosity. The reflected light was polarized, a telltale sign of metallic surfaces, not dusty ice. Even stranger, the pair maintained their separation with mechanical precision, as if tethered by invisible mathematics. Then came the revelation no one was ready for. An independent research group in Finland cross-correlated the 22-second radio pulse first recorded during the blackout with archival data from 2017, the year of Oumuamua's passage. The result? A perfect harmonic multiple. Valkyrie's signal was exactly twice the base frequency once attributed to transient solar noise during that earlier interstellar visit. What everyone dismissed as background interference now looked like a continuing pattern, as if each visitor were a note in a cosmic sequence. In other words, someone, or something, had been playing a message through the solar system for nearly a decade. Governments moved swiftly. NASA and ESA convened an emergency joint task group called Solar Gate Initiative, coordinating with China's Deep Space Network and the Indian Space Research Organization. Officially, their purpose was to assess interstellar debris trajectories. Unofficially, leaked memos showed an entirely different goal: to make contact. A probe concept was rushed from design to launch readiness in 6 weeks. Codenamed Project Hermes, it was based on a repurposed solar sail demonstrator designed for extreme velocity flybys. Its target, H1b, the smaller flashing companion, predicted to pass within 0.08 AU of Earth's orbit by mid-October. The plan was audacious: intercept, image, analyze, and, if possible, transmit. Hermes launched from the Guiana Space Center on September 29th, atop an Ariane 6. Its sail unfurled perfectly, using solar pressure to accelerate beyond 120 km/h. Public coverage was minimal. The mission was buried beneath euphemistic press releases about solar debris monitoring. But in encrypted circles, astronomers followed every telemetry update. October 12, 2026, Intercept Day. Hermes approached within 3,000 kilometers of H1b. The probe's cameras sent back a handful of images before its transmission abruptly cut out. Only fragments of data survived, but they were enough. The images showed no irregular rock, no jagged ice. H1b was smooth, geometrically smooth, an ellipsoid roughly 45 meters long, composed of hexagonal panels that shimmered like molten silver. The surface radiated faint heat at 310 Kelvin, room temperature. Across its center ran a dark line, like a seam or aperture. In the milliseconds before signal loss, Hermes detected a brief electromagnetic burst, a structured tritone repeating sequence, 22, 11, 5 seconds. The same harmonic ladder found in Valkyrie's pulse and Oumuamua's anomaly. Then silence. When Hermes failed to re-establish contact, ground stations assumed vaporization by solar radiation. But 2 weeks later, long after its expected destruction, a single compressed transmission arrived, not from Hermes, but from deep space, along a trajectory exactly opposite to its launch path. Inside the burst packet was less than 10 kilobytes of data, a single grayscale image, faint and corrupted, showing what appeared to be a star map. The coordinates matched the sun. The image was time-stamped 22,554 years earlier, the same orbital period once calculated for the legendary comet Swan of 2025. Scientists stared in disbelief. If genuine, the signal implied that Valkyrie, Swan, and perhaps even Oumuamua were part of a recurring cycle, returning at intervals that predate civilization, and that each visit was recorded, logged, and relayed outward. But outward to where? Historians and archaeologists were drawn into the debate. At Göbekli Tepe, Turkey, a set of engravings long thought to represent constellations was re-examined under new light. One panel, the so-called vulture stone, showed a cluster of circles and a curved path crossing what appeared to be a radiant sun symbol. When astronomers overlaid the diagram on orbital reconstructions of Valkyrie's passage, the alignment was exact, right down to the 60-degree inclination. If the builders of Göbekli Tepe had encoded the path of a comet-like visitor, it would mean they had either witnessed it or had been warned to expect it. Speculation spiraled. Could Valkyrie be a relay, returning every 22 millennia to collect data from evolving civilizations? A galactic census probe, measuring progress, cataloging our rise from the ice? Or was it a seed ship, scattering micro-artifacts of its origin across habitable worlds to awaken memory. The data from Hermes hinted at something haunting. The tritone pulse, when converted to audible frequencies, produced a sound, a low oscillating hum followed by a short silence, repeating in perfect rhythm. Acoustic analysts mapped it against Earth's atmospheric resonances and found an uncanny match with the Schumann resonance, the natural electromagnetic heartbeat of our planet. The message wasn't just from the stars, it was tuned to us. By December, Valkyrie had crossed beyond Mars's orbit, dimming to magnitude 14 and slipping into the outer dark. Its twin drifted beside it, still flashing once per second. The world's media had moved on. Attention turned back to politics, wars, and economics. Only a few observatories kept their eyes on the receding light. Then, quietly, a final entry appeared in the data log from the Deep Space Network. At 0222 UTC, January 7, 2027, Valkyrie's signal flared once. A single narrow-band spike at 1.42 GHz, the hydrogen line, the frequency astronomers have long proposed for interstellar communication. The burst lasted exactly 11.7 seconds, the rotation period of its inner clock, and within it, a repeating numerical pattern. 1, 2, 3, 5, 8, 13, the Fibonacci sequence, the mathematics of life itself. Then the signal faded into the cosmic background, leaving only silence and questions that will outlive us.